Welcome back to the TST100 project. Obviously, we've got an engine now, and it's made of aluminium. We ended up 3D printing it instead of machining it from a billet. We talked about machining it in the last video, but there became some challenges. First of all, though, we're pretty sure that this is the first 3D printed aluminium motorcycle engine in the world that's going to be functional and make horsepower and actually work in a race bike. So that's pretty cool.
And if there is another one that we don't know, send it, I want to see.
Yeah.
We can't find anything.
Yeah, we've looked everywhere. We can't find anyone else that's successfully made a 3D printed aluminium motorcycle functional engine. So if you know of one, show us, because we want to learn. That was the whole point of doing this, because we're going to make a bigger bike. Everyone wants to know, is a 3D printed engine case or whatever, any 3D printed metal, is it strong enough? Is it going to fall apart? What are the issues with it? So tell us a bit about the material properties of the 3D printed aluminium, Glenn.
From a material composition, it's extremely similar to a cast aluminium, typically what you'd see in most engine cases and even piston stuff. It's pretty small differences, mostly in the copper content. I think it seems to be the biggest difference. The 3D printed aluminium is quite a bit stronger. So just for a context, LM13 cast aluminium, which is what you'd normally see cylinder heads and cases cast out of, is sort of in the 140 to 180 MPa for its yield strength. And that variation is because of the inclusions and inconsistency in casting properties that you have such a big window. Whereas with the 3D printing, the yield strength is a lot closer. The window that you work in is a lot closer. But what you do get is a difference in strength between its vertical and horizontal axes. And that's because of the way the layers are printed. This cast alloy is 230 MPa in a vertical pull and 270 MPa in a horizontal pull. So that shows you that difference of the layer stability, but significantly stronger than your typical cast aluminium. And when you're machining it, it certainly feels like it.
Tell us a bit about the dimensional stability, weldability, and part quality.
Yeah, so the manufacturer that printed them, they give you a pretty scary tolerance, which is 2%. So where a case is like 300 mil, so that's 6 mil over that they're saying it could be. So, that was a little bit of a gamble. Because if it came in 6 mil short, it would have been up shit's creek. But it's remarkably dimensionally correct in some planes, and then weirdly odd little bits in here and there have moved, and it doesn't seem to make a lot of sense. So anywhere there's like a flat surface where the bearings are for the gearbox and everything's on one plane, it's within 0.1, 0.2 of a mil across that distance. It's, as good as you could imagine. But then in other areas where the case halves meet, it's a bit warped on those small thin surfaces where I guess maybe it gets a bit more shrinkage there. So that caught me out a little bit. But I think for the bulk of it, all of our bolts go through the holes. So I think that sort of tells the story. Yeah,
so the part fundamentally is as good as you would find a cast part, which is awesome. Considering that it was a complete unknown, obviously when we were looking to do it, we tried to find some examples of someone that had done it before so that we could avoid making the same mistakes that anyone else has made. We couldn't find anything, so we kind of just took a stab in the dark.
I just didn't put enough meat around the lugs on the engine cases. I don't know why I made them so small. They're just more delicate than they need to be.
Yeah, but if you snap one of these lugs, you could just weld and then drill and tap the weld, right?
Yeah, the stuff. I haven't welded it myself yet, but I've seen other people fabricate other parts out of it, and they say weldability is really good. Cool.
Hamish asked us a question, which was, how do you determine the torque settings? Because it's obviously not a stock motor that has an instruction manual. It's all just, you've made it. So how do you tell how to torque your bolts?
So mostly just first principles of engines and well, actually less to do with engines, just bolts. So bolt manufacturers, they specify a torque range for their bolts. An M6 cap screw is somewhere around the 8 to 10 Newton meters. M8 sort of like 15 to 20. So that sort of tells you, like if you've got an M6 bolt holding something together, then you set it to that window. That's where you want to be. And then most of the other stuff in this engine, the only other sort of torque critical bolts would be cylinder head, but I'll just set those to what they recommend from the factory, because that's more to do with the cylinder head clamping force rather than anything to do with the cases.
As we talked about previously, fuel injection. So these are just open throttle bodies, no carburetors. And then we've done a, what is it, TPU, 3D printed intake, and then into V-Force reed blocks. Pretty simple, really. And, you know, end of the day, if the fuel injection doesn't work, we just put carburetors on. But it's going to work. So you can also see here, we put just a normal KTM clutch slave cylinder, which was, again, you just got a 3D model and yeah.
Yeah, I got stitched up. The original design, I had downloaded the 3D model off the internet and it was fucking wrong.
Yeah.
So luckily we tested the plastic 3D printed cases.
Yeah.
That's what showed that it was wrong. So then by that time I had actually ordered and received the final part. So I just 3D scanned it and yeah.
Yeah.
That's another thing. So some of the real nerdy details, but this is just shows you how far 3D scanning has come. On the clutch side of the engine here, to get the bolt spacings for those was straight off the 3D scan, straight into SolidWorks. I never put a ruler, nothing, a vernier, nowhere near it.
Yeah.
And then that's what derived the case geometry, and then that went and got 3D printed. Yeah. And I've never touched it, and all the drilling holes are all 3D printed into it, so you're not drilling. All I did was tap the holes and bolt the thing on. And again, all of these holes are only 6.2 mil drilling for a 6 mil bolt.
Yeah.
So
it's literally perfect off the 3D laser scan.
It's amazing. It's just game changing.
Like Glenn said, we used the FZR stock clutch cover because we got the same stock FZR clutch and gearbox and everything. So it makes sense to just put that on. Gives us a nice oil filler cap as well that we don't have to make. Yes. The biggest question that everyone has had so far is, what does it cost? And is it worth it? So
as far as our wives are concerned, $20.
Yeah. Yeah. So what does it actually cost, Glenn? What did it cost to get these printed? Obviously, we're not counting the labor in designing the cases, which would be the biggest cost if you were paying someone to do it. But just to manufacture the cases, what was the cost difference?
A tickle over 3,000 New Zealand dollars.
Yeah.
Yeah. So I'm glad there's three of us going in on this, because otherwise this would suck.
Yeah.
But you got to put it in context. So part of the reason we went away from doing the billet machine cases where they were going to be the same price, but that wasn't as interesting to me because heaps of people have done billet machine cases.
Yeah.
So this is about learning and doing new cool shit. And for future projects, this is an avenue that I wanted to know whether is a viable option. So I was like, if the billet cases were going to be half that price, then I would have gone with the billet cases. But given they're the same price, I was like, no, we'll try it and see what happens. And, because there's so many things to test with it, fatigue resistance, is it going to crack? What's it going to do? How's it going to move when it's under load? Like, there's just a lot of, things that we don't understand about applications of 3D printed metal in an engine environment, which is a brutal environment. It's hot, it's cold, you've got huge thermal discrepancies, and then vibration and high loads at temperatures, and it's a pretty nasty environment for a material. So yeah, we're the guinea pig. Yep.
Pretty exciting though. It's pretty awesome. Yep. Like I said, probably a world first as far as we can tell. Let's hope it doesn't explode.
Well, it's weldable, so if it does, we'll just glue it back together.
Yeah. Especially as I'm going to be riding it, so hopefully I don't get a piston up the arse, but, we'll see. We're going to do some video taking it apart and just show you sort of how it all fits together. Before that, though, we haven't actually talked about the machining that you need to do. So obviously you get it 3D printed. It's not perfectly, to the final dimensions, so you need to machine it and that sort of stuff. So what machining have you had to do to get it to actually accept bearings and so on?
Yeah, so I just used one of my neighbours. He's got this little tiny mini lathe mill combination that's really not the correct tool for this job, but it kind of was a fun challenge for me just to see what I could do with some pretty rudimentary tools. So all of the bearing surfaces and seal surfaces I left 1 millimeter of material on. So that gave me, if there was a bit of shrinkage and stuff, plenty of meat to work with. So it was just a matter of going through and just with the boring head, opening those up. Yeah, lots of old school machine work because I don't have a dial readout, a digital readout or anything. So trying to accurately get my shaft centers on it was a bit of a trick. Seems to be pretty good. The gearbox is in there, and the spacings and the shift drum and everything seem to work pretty right. So it's kind of, it'd be the same, sort of similar if you had a casting. You know, you can't rely on the 3D printed surface as a finished bearing surface or seal surface. Probably took 20 grams of material off it, and the whole engine, it's bugger all. Yeah.
So it's pretty close to final dimensions when you get it off the printer. And it's worth mentioning these were printed in China and sent over from there, because they are about half the price of anyone else in the world.
Oh, try 3 times. Yeah, I think a non-China quote on the online was like 10,000. No, even 10,000 US dollars.
Oh wow! So
it's just like, the only reason that this is possible was because China's decided to undercut, and honestly, they're probably running at a loss at the moment. I'd say. I'd hate to think how many hours it took to manufacture these in their machine. They
don't just print it like this, they print it with all of this support material that I think they use AI to work it out or something like that. And then they got to remove all the support material, which, on a plastic 3D printer is easy. You just snap it off with your hands. But for aluminium, it's a bit more involved, right? So there's still a bit of labor involved. You don't just come out of the printer and it's ready to go on the boat.
This is around a corner, which you can't machine. Yeah. And you can still feel some of the support structure in there because they can't get tools to grind it off.
Yeah.
So there's definitely probably a good couple of hours of just post-processing once it's printed.
$3,500 that's really cheap when you think about what you're getting for it, to be honest. Glenn's going to finish machining and assembling the motor, and then it's pretty much go on the bike, put a tune on it, and go to the dyno and get it to run.
Wow, it's a bit of work between there, mate.
Yeah. That's fundamentally that's what's left, but there's heaps of wiring and programming and lots of assembly to do. I can't understate or overstate how much work it is to not only design and manufacture an engine from scratch, but then foolishly also do a fucking chassis at the same time. Just the thousands of little parts that would add up over the project, But because of that, and because of how it's been designed, this engine, for comparison to an FXR 150, which is another competitive bucket bike, the engine's about half the weight and should make more horsepower. So it's worth it.
Yeah, so a tickle over, fully assembled with every bearing, seal, you name it, the whole engine assembly. Although I did have the throttle bodies and things on it. It was a tickle over 18 kilos.
And the chassis is light as well, so it should be light with lots of power and go fast.
Yep.
Otherwise, we're wasting our time. All right, cool. Let's go and take it apart and show you what's on the inside. Sweet as. Little turbo CBR 100 contraption. Here we are in the garage, pulling this thing apart.
Rip it apart and you can see how it sort of assembles by the unassembly. If you want to watch the assembly, play this video in reverse.
Cool. All right. Rip it apart then.
Yeah, there you go. So we've got one crankshaft. We'll grab a look at the old. Oh, that's satisfying.
Yeah. Obviously the piston's a bit high in the bore at the moment. Needed to space the bore up.
Yeah,
none of the cylinder up.
None of the port timings have been done yet. No, get spaces and whatnot underneath them to fit it all up. So what do they call it? It's Instagram ready. There you go. Tiny little sucker.
50cc cylinder times 2.
The way we're going to do the throttles, because we've got 2 throttle bodies, and to get clearance they're actually angled at 45 degrees, which is why they look kind of funky. But just going to use an old school cable splitter like what you would on a twin carb 2-stroke like my NSR 300 has, and just have one cable go to each throttle body, and then
and then a TPS on one of them.
Yeah, this one here will have a TPS on it. Just use one TPS, so we'll be fine.
And then we've got 3D printed TPU little manifold here, which Glenn's taken off. Fuel stable and flexible enough to.
Yeah, they swell a little.
It.
They swell a little bit with fuel, but not too bad. The black seems to be the best for some reason. It's better than the other colours. But this will get a aluminium clamp plate because obviously it's a bit soft to just bolt straight on. You'll get air leaks, so there's a clamp plate to seal it up against that. But just trying to keep the intake tract as short as possible. So these here will also get machined shorter, just to try to take the length out of the intake.
Yeah,
up to
the shortest distance between the outside air to the reeds, basically.
Yeah, yep. Another cool little detail with 3D printing, so that's our crank trigger you know, and the lugs all just molded into it. So it's like, usually these things here look like shit when you put them on other bikes because they're always on some janky bracket. So it's nice to have something actually
just made for it,
integrated into the thing rather than some ad hoc.
And that's just a Hall effect sensor, right?
Yep, yeah, just from Haltech. Just a normal crank or cam angle sensor.
So this is one of the 3 pieces of the crankcase, and that caps that side of this crank, right?
Yeah. Yep. So you'll see in a second the crank will come out with it.
Yeah, and you can see some of the intake port there.
Yeah, so that's where the reeds come down and live inside there, and fill your transfer duct up, and yeah, again, like I say, that's all just copies of existing engines.
Yep.
So it's all pretty straightforward.
So why have you not made the crankcase volume larger?
So it's kind of, there's a window that works basically. I think it's like 1.32 or something like that seems to be the magic number.
Yeah. And what does that 1.32 mean?
So that there's the ratio of the cylinder volume to your crankcase volume.
Yeah.
So 50 cc, so then you're like, whatever, 1.32 times that is like 70 cc or something.
Yep.
Yeah, that seems to be the...
And that's the crankcase volume we've arrived at.
Yeah, yep.
So here's inside the next case, and you can see again there's that intake port, or duct or whatever you want to call it, and the transfer port there, and you've machined out the seat for that bearing there.
Yeah,
right?
so this here is where the core will go, and this is what will house all the crank coupler and bits and pieces inside there. So I'll actually have to drill a couple of access holes for tightening up the coupler, depending on what design I go with.
Because you can't get inside there.
Because you can't get inside this. So the cool thing about 3D printing, so again, I've manufactured something that you can't machine, and this is all pocketed cavities inside.
Yeah.
So
you can make it lighter than if it was CNC.
Yeah, because you just...
We didn't mention that in the studio, actually. This 3D printed case is lighter than what the CNC case would have been.
Yeah, quite a bit, because of all of the, again, like in here, you know, there's material missing here that just I've been able to pocket it out.
Yeah,
So
you can't do that.
You can't get a tool there.
Yeah.
You know, in a normal machining environment.
Yep. So there you go. There's another advantage of 3D printing that you don't get from a billet machine case. I mean, you might get some similar advantage with casting.
No, casting's sort of similar to machining because you have to be able to get your cores and your plugs, everything. You need access to everything. And then casting's also different in that you have to have relief angles on everything. So everything has to taper away so that you can get the part or get the plug out of the sand, or you know, if you do it that way. I think I've never done an investment casting. I think you can do some other geometries, but
so out of the 3 manufacturing processes, 3D printing will yield the lightest crankcase, theoretically.
Yeah, I think so. Yeah, because you can just make sure the material's where it needs to be.
Here's a bit of a look down that intake there.
Yeah,
so that's where the reed sits.
So all of this gap you can see needs this is where all the gearbox needs shimming, and then I need to put that 0.9mm space of shim, and there's still lots of work to do with just getting everything set up correctly. That's going to take there'll be a little bit of fettling, and that's just the nature of a not production engine case, you know, where they've gone through and solved all the little problems.
Yeah.
Some of it was quite hard to judge, inserting this gearbox into a vertically split crankcase coming out of a horizontally split crankcase. It's quite hard to figure out exactly where the gearbox shaft center lines want to be in relation to the shift drum and things like that. So it's just going to take a little bit of time with some shims just to get that all bang on.
Look at that stock FZR 250 clutch cover.
Yeah.
Over the top of a stock FZR 250 clutch, and that big ring gear there. You can see in the inside, where it would pick up on the crank gear. So the crank gear comes out of the crank there, obviously, and it will run on that big ring gear on the clutch.
And then this will just be a plastic 3D printed cover. And then now this is one of the coolest parts that I reckon Yamaha came up with for the clutch. So you can see this big ring gear disappears behind this cover, right? So you can't get the clutch out. I love shit like this. So they have a little hub that you just pull out of the clutch, and it comes out, yeah, like so, and then the bearing comes out, and then that lets you tilt the thing out sideways. So this is another cool 3D printed part. You know, like you can't machine that. That's a you know, you can't even really. You could investment cast that, but you couldn't sand cast that, not easily.
Yep.
I think maybe, I don't know. So yeah, this is the clutch side of it is pretty much identical. The only little funny bit is in the horizontally split cases, it uses snap not snap rings.
To go on here even.
Yeah, circlip grooves to locate the bearings and stop the shafts walking around. Because we can't drop in, we're coming in from side, it means that I have to use shoulders. So this shoulder here, you know, it's 2-3 mil thick, I think. It just pushes the clutch out because I'm going to have to put a spacer in to meet this. It pushes the clutch out by that distance.
Yeah. So it doesn't run on the case.
Yeah. So it doesn't really affect anything. It just means a little tiny bit less thread engagement on the hub nut, but I think it'll be fine. We can work with it. But yeah, all the
stock Yamaha shifter and shift drum and everything all fits exactly as stock.
So that's neutral there. I think one of the ways it should go into gear. There you go.
Nice.
Neutral. Yeah.
These are all just standard fasteners off the shelf, eh?
Yeah, just went and ordered them.
Crankcase.
Crankcase, yeah, so this is the biggest part of the 3D printed part because it's the main core. And then,
Yep. There's your gearbox.
And there's your gearbox. And that's really the guts of it.
Yeah.
It's,
another bearing seat there for the crank.
It's just quite satisfying. See the crank in there with the
piston and rod on it. Yeah. Beautiful. And then that goes round and round at 16,000 RPM. Have a look at the word collaboration though. What happened there, Glenn?
What are you talking about?
This guy can design an entire engine on CAD by himself, but can't spell collaboration.
Fuck!
Adds character. TST100, model number 001, 2025.
It's how we'll be able to tell if they ever get counterfeited, mate.
Yeah.
The counterfeits will fix the fucking spelling.
Yeah. If the Chinese come and laser scan this motor.
Well, they've got the CAD file, man. They can do that.
True, they don't need a laser scan.
This shit's in production now.
Over here, the chassis is nearly done. That little thing on the top is just a cap for the fuel cell. This will all be anodized black probably when you guys see it on the track. Powder coated, sorry, not anodized. Going fast as. Ollie, what do you reckon? Cool.